can start. All right, good morning everyone. So today it's going to be very short. Okay, I know that maybe you are a little bit excited and a little bit tensed about your quiz, right? So I'll make it very short, and then maybe we can have 10 or 15 minutes if you have any question, like regarding the topics that we covered in last 4 days. Okay. So I thought actually today's talk, it's going to be on conventional and emerging techniques or methods for enhancing anaerobic digestion process. Although we covered anaerobic digestion process, I thought it's better to give some insight or perspective on what other stuff are going on in this industry, and what different methods we can use actually to improve anaerobic digestion process. So I'm gonna cover 3 topics here. So one is thermal hydrolysis pre-treatment and microaeration. Actually both of those topics have been technologies have been implemented in full scale, but still there are like research, a lot of research going on for both. And under emerging technique, I'm gonna cover one topic, conductive additive direct interspecies electron transfer. Some of you actually also attended my research seminar, so I talked a little bit, and like if you have missed, so you are going to have some information on that. So one of the like common bottleneck in anaerobic digestion process is slow hydrolysis. Okay, so because anaerobic digestion mostly used for complex organic waste. Okay, so where you have like most of the organics, they are actually in particulate form. Okay, so if you think about like municipal sludge, okay, that we use for anaerobic digestion process, one of the major problem of activated sludge is kind of biomass, right? So biomass, and sometimes biomass actually they form a like very I would say like a strong network of different polymeric substances. And during anaerobic digestion process, it's very difficult to actually break down that polymeric network. So that's why like one of the common challenges, you have to provide higher residence time to actually make sure that you have enough hydrolysis of your organics, and you can actually recover them in as biogas. But sometimes it may not be actually feasible. Okay, for example, like so typically residence time for anaerobic digestion process, it's from 3 to 4 weeks, right? So and 3 to 4 weeks you might end up with like 40 to 50% solid removal, which is kind of not desirable. And like if we provide more solid residence time or hydraulic residence time, it's also going to actually increase the digester footprint, right? And also actually it's a big capital investment. So that's why actually a common approach to enhance the hydrolysis process in anaerobic digestion is pre-treatment of feedstock. So before actually you are feeding the like waste into the digester, you can do some sort of pre-treatment. So pre-treatment, basically you break down the particulate organics to you basically solubilize and release the organic in liquid phase. So microbes actually can easily access them and convert them into methane by fermentation and methanogenesis process. So and there are different techniques that we can use. Okay, so thermal hydrolysis by conventional heating and microwave, but conventional heating is much more popular. Microwave, it's still in research phase. There are other techniques that have been actually like studied in lab scale. For example, ultrasound, you can actually use ultrasound generator and create hydrodynamic like a cavitation bubble. Okay, so those cavitation bubble, when they are going to actually collapse, okay, they are going to actually create a very high hydrodynamic shear force on the feedstock. Okay, and those feedstock can be solubilized. There are other techniques, like you can use mechanical jet, basically depressurize the and sludge from high pressure, high pressure homogenizer, mechanical ball mill, some other technique. Sometimes chemical pretreatment have been used. So for example, you can use strong acid or base or some advanced oxidant like hydrogen peroxide, Fenton reagent, like yesterday I was talking about Fenton reagent, peroxide plus iron salt. Sometimes ozone can be used, okay, and sometimes different types of actually pretreatment method can be combined together, okay, to further boost the process. But among those actually pretreatment method, only thermal hydrolysis have been actually implemented in full scale. So why only thermal hydrolysis have been implemented? Okay, so if you think about like chemical pretreatment, if you want to apply chemical pretreatment, you always need to buy, okay, those chemical, and there is no way after the pretreatment process you can actually recover them. And you know that especially after COVID, supply chain disruption actually a very concern like worldwide, right? And price of lot of things and chemicals have been actually increased, not only because of supply chain issues like inflation in many countries and some geopolitical issues, right? So chemical pretreatment often it's easy, but it can actually you need continuous supply of those chemicals. Mechanical pretreatment, sometimes it can be effective, but energy investment for running those mechanical processes can be really expensive. But what thermal hydrolysis can provide, what more benefit we can get compared to other method that we have, okay? So one of the major reason why thermal hydrolysis process actually has been implemented in full scale, the main reason was actually we can recover like after pretreatment process is done. So basically like you are pretreating the sludge at about 100 or 150 degrees Celsius. But if you think about anaerobic digestion process, at what temperature we run anaerobic digestion process? You remember? 35 mostly mesophilic, right? But your after pretreatment process, it can be pretreated sludge temperature can be about 150, right? So you cannot actually like feed that 150 degrees Celsius temperature sludge at 150 degrees Celsius to the digester, right? Because you are going to kill all the microbes if you do that. So that means we have to cool them down, right? So you can use heat exchanger, and actually you can recover the heat from that pretreated sludge, okay, and that heat can be actually reutilized in the process. So that's why that heat recovery kind of make this higher thermal hydrolysis process economically more feasible compared to other pretreatment method that you have, okay. So for example, if we use sludge at high temperature, what we can do in sludge, it's mostly extracellular polymeric substances you have in your sludge biomass, and they kind of form a very kind of flock and very strong structure, which is kind of difficult to hydrolyze by microbes. So when we use actually thermal hydrolysis, we can actually break down this network, okay, and release we can have cell lysis, and we can have the release of those intracellular organic compounds to liquid phase. So for example, like waste activated sludge, this is actually difficult to digest compared to primary sludge. And why? Because waste activated sludge is basically the biomass that is generated from during activated sludge process, right? Microbes, they utilized organics, they produce new cells, and sometimes break down that cell can be difficult. So that's why thermal hydrolysis can be used to actually kind of break down those cells and release the intracellular polymeric substances. So thermal hydrolysis if we improve the hydrolysis, we can actually improve the biogas production as well. But thermal hydrolysis can provide other benefit. So one thing is we can also improve sludge dewaterability. And what is sludge dewaterability? Because if you remember, we discussed that actually before you send the sludge to the digester, you have to do some sort of thickening, right? But if you have very high EPS content, sometimes those sludge is difficult to actually settle, okay? So thermal hydrolysis has been actually found that actually it can improve the dewaterability. So even after the digestion process, before you go for land application, you have to actually remove the water and basically separate the sludge solid for land application. So thermal hydrolysis can help with that by improving the dewaterability. It can allow the heat recovery. It's like, as I just mentioned, and this is actually why it has been implemented in full scale. It also actually enhances the digested quality for land application. So it has been found that actually when you apply thermal hydrolysis, it can actually, the digested quality, you have less amount of pathogen compound. Okay, so less amount of pathogen, so that means you can possibly get high quality of biosolid that can be directly applied to the land. So typically, from if you go for mesophilic digestion, the digested quality is not good enough in most cases for direct land application. So you have to do some sort of like further stabilization process. Okay, so like composting process, and then you can actually use it as a biofertilizer. But possibly thermal hydrolysis process, if you use, you can directly use the digestate for land application. And in recent report actually also actually found that some of the emerging contaminants like nanomicroplastic, antibiotic resistant gene, they can be actually removed using thermal hydrolysis process. But still there are some challenges in this field, mostly when you actually when you pre-treat the sludge at very high temperature, like at 150 or 160, sometimes what happens, some of the organics, they actually form at high temperature, they form some recalcitrant or some inhibitory compounds. Those compounds, although they are solubilized, they are in soluble form, but sometimes they might be toxic to microbes. Sometimes even actually some of those compounds actually cannot be degraded. Like the primary idea of having pretreatment process is we basically convert the particulate COD to soluble COD, right? So soluble COD can be actually utilized by microbes. But now what happened, you have those soluble COD, but they are very recalcitrant. So although you are doing pretreatment, it's not sometimes not helping that much. So sometimes those compounds can be formed. Okay, so that over long term operation, it has been found that actually digester microbiome, they can adapt those compound, but still they may not be actually efficiently degraded. Okay, so that's a problem. And another problem is high ammonia level in pretreated sludge. So in most of the complex organic waste, what we have carbohydrate, we have protein, we have fat, right, or lipid. So when you hydrolyze the protein, you release a lot of ammonia in the process. Okay, so that can actually be problematic in this kind of process. So but so far actually there have been several commercial products available if you want to use thermal hydrolysis for ready facility. For example, Chembi was actually first developed in 1995. That's a batch process, and it's operated at 160 to 180 degrees Celsius for about 30 minutes. And then in early 2000, between early 2000 to 2016, actually you can see there have been some other commercial processes available. Although this is in batch, you can see recently there has been a lot of interest on developing continuous process for thermal hydrolysis. But one of the thing possible you notice that actually most of them are have been actually developed in Europe. So that's actually another thing. So Europe, most of the countries, they have limited land space. Now most of the cities, population is growing, right? If population is growing, then you have more wastewater production. Again, you have more sludge production. So everything is like connected, right? So if you have more population, more wastewater, more sludge, more organic waste, then those existing, even if you have existing digester, it cannot actually accommodate, or they are not ready to treat that increased volume of sludge or increased amount of your organic waste. Okay, so that's why this kind of process can actually provide an unique opportunity for process intensification. So basically, these reactor footprint are typically very small. Okay, so what you can do, you can actually apply them, and with existing anaerobic digestion facility you can treat more waste. Okay, so that's actually kind of one of the common problem. And even in Canada right now, actually, for example, like I can tell, the wastewater treatment plant in our city is actually most of the time in wastewater treatment plant, they are very close to river. And why is that? Because after you treat, you kind of wanna dump the wastewater, treated wastewater, to the river, right? So in our city, the wastewater treatment plant, it's very close to river, and then after that there is a park and then residential community. So there is no other footprint left, then actually they can build new facilities there. Okay, so now actually what would be option? But population is growing, okay, significantly. Wastewater generation rate is getting actually higher, and sludge production is higher. So in that case, this kind of actually technique can be very effective approach. Okay, but so far I think worldwide there are actually at least, I think couple of years ago I saw that the number was about 75 installation of this kind of thermal hydrolysis process in AD facilities. Right now it could be more. Even I know that in Canada at least 2 or 3 facilities right now they are in design and construction phase. So CAMBI is kind of, it was developed in 1995, so they have actually more installation worldwide. I think at least half of them are CAMBI in most cases. So how CAMBI works? So CAMBI, it's the process actually uses stepwise heating. Okay, so you can see they have a something called pulper, where you preheat the sludge. So sludge coming here at 12 degrees Celsius, and they are actually preheating that at 90 degrees Celsius. Okay, and then they apply steam in the second reactor, where actually the main thermal hydrolysis happen. So when you apply steam, actual temperature reaches about 165 degrees Celsius, and then in the third tank, what they do, at high temperature pressure, from sludge at high temperature pressure, they are released, they are depressurized in the flush tank. Okay, so the process can mostly, even during anaerobic digestion process, you can possibly solubilize almost 40 to 50% of the VSS before digestion. Okay, so typically for if you run an anaerobic digestion process at residence time of especially for sludge, if you do it at solid residence time of 21 days, possibly you can get close to 50% solid removal or VS removal. But if you can actually kind of solubilize them before digestion, think about actually how it can actually increase the capacity of the system. So possibly you can shorten the solid residence time from 21 days to even let's say 21 days to 11 days, okay, or 10 days. So it's almost you are reducing the solid residence time by 50%. So 50% reduction in solid residence time mean you can actually treat double of your, like the you are actually basically enhancing the capacity of your existing facility by 50% or 100%, right, if you double. So first this kind of facility was installed in North American DC Water, actually very large facility. Facility can treat about 450 dry ton of sludge. Okay, but one of the major challenges is capital investment for this kind of process. Okay, so you have to pay like upfront, and it's a significant investment. For example, DC Water, this project was about $470 million USD. Okay, so it's a very high cost process. So the next topic, I talked a little bit about also sulfide, like when we are doing the theoretical calculation for methane potential for organic waste. You remember that in reaction there was one product which was hydrogen sulfide. Okay, so we had methane, carbon dioxide, ammonia, hydrogen sulfide. So sulfide is something actually very problematic when you want to use biogas, okay, to generate heat and electricity or some other purpose. Okay, even if you want to convert biogas to renewable natural gas, and possibly you all are familiar that now renewable natural gas project is actually getting very popular. Okay, not just in developed countries, even countries like India, it's getting very popular. But what we have in our biogas, we have 40 to 70% methane and 30 to 50% carbon dioxide, and we have sulfide. Even they are at very small concentration. In addition to sulfide, actually you can have some other organosulfur compounds like mercaptans. Okay, so even they are in small concentration, sometimes they can be very problematic. Okay, so they can actually corrode the process equipment. So if you want to convert biogas to renewable natural gas, okay, then first, so the common technique for converting biogas to renewable natural gas is pressure swing adsorption. Okay, so the process actually remove carbon dioxide from the biogas. But if you want to use biogas in that pressure swing adsorption process, you have to make sure that your biogas is free from any sulfide. Otherwise, it's going to be very problematic. Okay, over the time, it's going to actually corrode the process equipment. So in most cases, industry what they do, they go with, after the anaerobic digestion process is done, they do some sort of like cleaning of biogas to remove sulfur. Okay, and those ex situ processes, okay, mainly focused on adsorption, and sometimes even biofiltration process is used, but they are quite expensive. Okay, so that's why, like sometimes what happen in most of the AD facilities, okay, so they treat sludge or any other organic feedstock, but they end up with actually flaring the biogas. Okay, so they kind of maybe did some economic analysis and found that, okay, you know what, it's quite expensive when you actually treat the biogas before converting it to RNG, so it's not economically feasible. Okay, so that's why actually in last couple of years use of microaeration, okay, microaeration has actually become very popular area of research. So what is microaeration? We know that anaerobic digestion process is it's anaerobic, right? We don't need oxygen in there. And we know that actually anaerobic microbes, they could be sensitive to oxygen, right? If you have high DO, that can be actually problematic for their metabolism. But it has been found that if you have a small amount of oxygen in there, that can actually instead of negatively affecting the process, it can actually help, okay, the process. So how it can help? So this is conventional digestion. It looks little complicated, but don't be scared. It's like same thing that we learned in our class. You have a complex organic compound, okay, then you break down the biopolymer to simple sugar, fatty acid and amino acid, and then you have volatile fatty acid, and then you have carbon dioxide, acetate, hydrogen, right, and then finally you have methane. So same process that we have in conventional anaerobic digestion process. But what happen in microaeration? So if you have oxygen, oxygen can actually stimulate the growth of facultative bacteria. Okay, so those bacteria, they are known to actually hydrolyze the substrate easily. Okay, so they have actually much more capability of hydrolyzing organics. So if you can actually improve the those microbes, okay, they can help with your hydrolysis. And then after you have the hydrolysis process done, okay, so hydrolysis process actually produce different types of soluble organics. Okay, at the same time the process also actually produce hydrogen sulfide. So for example, if you break down the protein, you have different types of organosulfur compound. And at that time another thing happen. Okay, so when you have soluble organics, okay, sulfide reducing bacteria, what they do, they use some of those soluble organics like VFAs, okay, and they convert those sulfate to hydrogen sulfide. Okay. So, we learn in, I think in very first lecture, that sulfate reducing bacteria, they use organic acid as their electron donor, right, and sulfate as electron acceptor, and convert sulfate to sulfide. But if you have oxygen, okay, what can happen? So, some sulfur oxidizing bacteria, okay, they can utilize the oxygen and they can actually oxidize hydrogen sulfide to either elemental sulfur or sulfate. But most of the time it has been found that actually elemental sulfur, conversion to elemental sulfur is kind of more dominant pathway when you actually provide little amount of oxygen in the process. Okay. And also some researcher claim that you know, like when you apply microaeration, you can produce different types of reactive oxygen species, and that can actually also help to mineralize some of the recalcitrant compound, and they can be actually degraded in the process. So, there are two options. Okay. So, either we can provide oxygen or air in the liquid phase of the digester, or we can actually provide in headspace, okay, in the gas phase. So, for example, we can actually directly inject air in the digester, or another option could be we can actually add that in sludge recirculation line, and that is kind of quite flexible. You don't need to modify anything in your existing digester, just maybe, you know, you one of the inlet you are going to actually attach some pump or blower, and that can be actually used for aeration. But the major problem is if you apply air directly in the liquid phase, some of the organics may be actually oxidized. Okay. So, but in anaerobic digestion process you want to recover the organics as biogas, right. So, basically you converting them to carbon dioxide and water by oxidizing. Okay. So, we may lose some of the organics that could be converted to biogas, which is not desirable. In gas phase, what we do, we can either inject the gas directly in the headspace, or we can actually have biogas recirculation, and we can add actually air or oxygen in the biogas recirculation line. And we can actually avoid, so that's how we are not actually you know, providing aeration in the liquid part. So, we can avoid some of the organic loss that we might have in liquid phase microaeration. But the challenge is for this kind of a concept, if you want to, let's say, directly inject air in the headspace, okay, you have to do some process modification. Sometimes actually, you know, like AD facilities, they don't want that. They don't want to touch the existing process. And another challenge is sometimes operator, they are scared of, you know, kind of providing air in the headspace, because methane is flammable, right. So, you know, you could have explosion if you have something happen. Let's say, you know, somehow your process control system actually fail, and you have very high oxygen injection in the process, it can actually, you know, cause fire, right. So, and another problem is when you have actually inject air in the headspace, sometimes those microbes, they form actually biofilm in the headspace wall, okay, and they basically, you know, convert hydrogen sulfide to elemental sulfur. So, that means you can have clogging issues as well over the time. So, that is why most of the time actually facility, they decide to go with liquid phase microaeration. Okay. And this is actually some example of full scale demonstration. You can see here actually this work was done in Europe in multiple AD facilities, where you can see digester volume was from 1600 to 30,000 meter cube, and Suez sludge they used, and they are actually hydrogen sulfide level actually was significantly varied from 700 to about 8,000 ppm, and they did actually they applied air in the sludge recirculation line and could go up to actually 99% sulfide removal. Okay. So, this is actually another technique to actually watch out for. Okay. They are going to be, even actually we are doing some pilot scale study on this right now. So the final topic for today, so this is like more emerging topic, okay, in anaerobic digestion process. We call it direct interspecies electron transfer, okay. So what is direct interspecies electron transfer? Direct interspecies electron transfer mean when microbes, they directly exchange electron, okay. So we know that in anaerobic digestion process, what is anaerobic digestion process? It's a multi-step biochemical process, right? First you hydrolyze the organic, then you have fermentation, and then fermentation product is used by methanogenic archaea, right? And you have one process is called acetoclastic methanogenesis, that is actually use acetate, acetate is converted to methane and carbon dioxide, and the other process is hydrogen trophic methanogen, like that process use hydrogen and carbon dioxide and convert it to methane, okay. So that's actually kind of like we know for over like anaerobic digestion process has been used for I think 60 years, more than 60 years right now, right. So 50 or 60 years, and we know those conventional pathways, although previously methanogen, they were known as bacteria, and now we know they are archaea, but regardless of this, we know that actually those are some of the common pathways. Then actually interestingly, in 2011 one paper came out, okay, in like MBio journal, and they found actually, we know that actually in USB process, we learned about USB process, right? USB process, what happened? You have microbes, they form granule, right? So microbe, they form granule, and so they are very close to each other, right? They kind of attach to each other. So then that research group, what they did, they actually collected some granules, sludge granule, okay, and they did the actually from brewery wastewater, and they did the microbial analysis, okay. And interestingly, they found actually geovector species in this microbial community. Geovector species was, their relative abundance was really high, 24.5%, okay. And why that thing was interesting to them? Because at that time, like microbial electrochemical technology, that's the topic that I covered yesterday, okay. So this topic is already very popular, and we know that most of the time we see, like if we see any do any microbial community analysis, we see actually in anode biofilm geovector species is like abundant, and we know that actually geovector species, they can do extracellular electron transfer, right? They can actually transfer electron to some conductive solid material, okay. So then researchers, they became really curious, okay, why geovector species is there? Typically we don't see geovector species in, if you do any microbial community for anaerobic digestion process like conventional reactor, we don't see any geovector species. So what they did actually, they got some aggregate from granular sludge, and they measured the conductivity of the sludge, okay, and they found actually their conductivity is range from around 6 microsiemens per centimeter, and that conductivity is much higher than, if you remember yesterday's class, like conductivity was range from 1 to 2 microsiemens per centimeter, right, for geovector biofilm. So here conductivity is even higher. So then actually, and that was actually kind of like a breakthrough in this area, okay. So why? So they kind of try to further investigate, okay, why geovector species is there. So what they did, further researcher actually studies co-culture study. So co-culture mean they got pure culture stain of some geovector, and they added some methanogenic culture in there, okay, and they found actually some simple substrate like ethanol or acetate, okay, can be actually converted to methane, because we know that it was converted to methane, and that was kind of like because we know that geovector, they love to actually transfer electron, right. So when you have ethanol must be converted to kind of something else, right. So now researcher actually further this kind of multiple co-culture study confirmed that, okay, what, like those electroactive bacteria like geovector species can directly transfer electron to methanogen. So some methanogen, they can directly take electron. They don't need acetate or hydrogen. Okay, they can. So that's why, like, they call it direct interspecies electron transfer. So some microbes can directly transfer electron to another microbes. Okay, and this process is very, can be thermodynamically and kinetically more efficient, because when you produce a metabolite, okay, so the process is not kinetically very fast. Okay, or sometimes let's say interspecies hydrogen transfer, or when hydrogen is utilized by hydrogen trophic methanogen, the process can be limited by diffusion, right, because hydrogen is a gas. So now actually now the question is, we know that actually at that point it was kind of proved that, okay, in system like USB we could have direct interspecies electron transfer, okay, and that can actually make the process faster.
So kind of ohmic losses are less, that's why the current we are getting is more.
They are they are very close, but the question is, in conventional CSTR you don't have any granule, right? Microbes, they are not close to each other. Okay, so then researcher thought, okay, how we can improve this kind of, or kind of stimulate this kind of process in conventional digester, because USB mostly used for kind of industrial wastewater, right? But now what we can do to actually apply this kind of approach in other digester. Then, but again, before that, actually there are two types of mechanism you could have when microbes, they directly exchange electron, and I was actually discussing that yesterday. Microbes, they produce conductive nanowire, okay, and then they directly transfer electron, but instead of electrode, some methanogen can directly take them. Okay, so that's why we call them electrotrophic methanogen. Okay, so they are, like, we call heterotrophic microorganism, right? Use organic carbon. So here they use electron directly, we call them electrotrophic methanogen. So, and they can also use cytochrome. Okay, so when they are very close to each other, cytochrome kind of can act like a carrier. Okay, for so for example, like yesterday I was mentioning, when cytochrome is very close to each other, like within 1 or 2 nanometer, okay, one can be oxidized and other can be reduced, right? So then researcher thought, okay, how we can facilitate this in conventional anaerobic digestion process, and then they came up with an idea. Then they thought, okay, what if we provide some conductive material? Okay, so then actually microbes, they can form actually a biofilm in there. Okay, and even some microbes, they cannot do direct interspecies, like direct electron transfer like geovector species. Maybe they might be able to actually transfer electron or dump electron on the conductive material. Okay, so then lot of studies have been done with many conductive material, activated carbon, biochar. Okay, biochar also has conductivity, but less than activated carbon. Carbon cloth, magnetite, it's an iron based, right? Carbon fiber and different other composite material, and its most cases it was found that it can improve the process kinetics, okay, improve the biogas production. And the mechanism, initially it was thought, okay, direct interspecies electron transfer gonna be the primary mechanism, but there are other mechanism can also be involved in there, okay, that can also improve the process. So for example, if we use iron based conductive material like magnetite, that can actually react with hydrogen sulfide and you can actually precipitate them, right? So you would have less hydrogen sulfide in your biogas. Sometimes ammonia, high ammonia level could be problematic. So sometimes ammonia can be actually absorbed by those conductive material. Sometimes actually VFS can at high organic loading rate, some of the VFS might be problematic. Okay, so they can be absorbed, but other reason is when they are when you have this kind of conductive material, that can also allow you to actually retain some of the active biomass in the system more easily. Okay, and at the same time it can decrease the interspecies distance, right? So microbes, yes, some microbes maybe they still not going to use diet, okay, or direct electron exchange, but when they are close to each other, it can help like metabolite exchange easily, okay, compared to conventional digester.
So as per your experience, when we are adding
Yeah.
some of the conductive materials,
Yeah.
how much biogas in terms of efficiency we are
It's kind of like it's a wide range, okay. It could be improvement. Maximum, I would say, even some people reported, it can be doubled even
by using which material?
by using. I think GAC has been mostly used, granular activated carbon. Okay, some people claim that it's doubled. Okay, for our case, it was not doubled. Okay, but we most cases we have seen like moderate to high. Okay, so let's say 20 to 50%. Like in during my seminar, actually I was actually sharing some result. Okay, what we found about 20%, and 20% was we did it in bench scale, and even pilot scale we got 22%. Okay.
So you use carbon cloth, I guess.
Yeah, carbon cloth.
Along with the conductive material, we can also add geovector separately. The population.
Like you some sort of bioaugmentation, right? Yeah, like
Or maybe other micro. Now many bacteria are isolating.
Yeah.
Having nano.
yeah. So now previously it was only geovector and Schwannella. Now we know that actually a lot of other bacteria can do that, right? Yes, that could be a something that you can it. Yeah, it could be a good approach. But somehow they found actually this is easier because possibly bioaugmentation is going to take long time. But with addition of conductive material, you might see immediate impact. Yeah. So it's kind of a very hot topic of research right now. So after 2011, first paper came out, and first couple of years it was mostly co-culture studies. And after 2015 or 2016, it was boom. Like every year, lot of paper on this topic. But one of the major challenge is the cost of conductive material. Okay, what even we found. If you don't actually use those material for long term, at least for 6 months to 1 year, okay, the process is not feasible. So you can get improvement in biogas, but when you do cost benefit analysis, it's to make even break even, you need 6 months. Okay, so that means you need to use some material that is either low cost, very low cost, or it can be actually recovered easily. Okay, and that is something actually sometimes researchers are overlooking. They try to show the performance, good performance, but sometimes like we are overlooking that we need to make the process economically feasible if we want to actually take it to the full scale. Okay, and most studies so far it has been in it has been mostly in bench scale. Okay, bench or lab scale. Only few pilot scale studies have been done. Okay, I think not more than 5 right now. We just in high solid there is only one, actually our group we did that. So still we have to do a lot, okay, in terms of engineering development, and at the same time you also need to look into environmental risk. The good thing is it has been shown that if we add conductive material, it can help with sometimes removing the negative impact of some of the emerging contaminants. So for example, one study I was showing, like when we have nanoplastic, okay, and we add granular activated carbon, we have less amount of reactive oxygen species generation. Okay, and that can also improve the biogas production. So that's one thing. We also found that actually abundance of antibiotic resistant gene can be actually decreased. So when microbes they are immobilized, they kind of have less interaction for horizontal gene transfer. But that's not necessarily the case. Some studies also reported that when you add those conductive material, actually they can bump the or increase the antibiotic resistant gene level. Okay, and why? because then the researcher found actually it was not because of conductive material. It was because of, for example, in biochar you can have metal. So if you have high metal content, those metal can be leached, okay, and that metal can actually increase the selection pressure for increasing antibiotic resistant gene abundance, right? So that could be, so selection of material is very important. You are going to think about cost, at the same time you have to think about environmental risk. Sometimes what happen, when something works very well, we kind of are happy, we want to take it to the market, right? We think about cost, but sometimes we overlook the environmental risk of those compound, okay? So this is also very important. So this is all I had to share for today, and maybe 5 or 10 minutes if you have any question, okay, then we can discuss that, okay? Thank you. Thank you. So any questions so far?
Sir, what is carbon cloth?
Carbon cloth is a conductive material, but it's more like a textile, carbon textile. Yeah. So that is made from carbon fiber.
It is just a black color cloth.
Yeah. But it has conductive properties. Yeah.
Oh, it's not like graphene sheet.
No, it's not like it's like regular textile.
Regular
Yeah.
It's
Yeah.
visible. You can see.
Yeah.
Just like cloth, black in color.
Yeah, like I actually had a picture, but I did not bring the other slide today. But I think it has already been yeah.
Such seminar, I guess. you
Yeah,
have shown.
yeah. So yeah, carbon cloth, it's like a regular textile. It looks like regular textile, but it made from carbon fiber, which is conductive.
So in yesterday's session you talked about microelectronic central technologies. So like this technology diet which is electron transfer would be helpful in overcoming the challenges in microbial electrochemical systems, because here we see that the efficiency of electron transfer is significantly increased. Can you apply the system in the anodic chamber of the NEC unit to see the efficiency improvement?
Like what kind of efficiency?
Bringing this NFC into the real life application. So can we apply this DIT technology to increase the efficiency of electron transfer to the anodic chamber in the NFC or NEC technology?
Yeah, it depends on how, because typically, so diet is basically no connection, like right? But now if you want to use those material, actually like some of those electrode materials are made from this kind of material, like like you can have graphite rod, or even carbon cloth is has been actually even carbon fiber. So we use actually a lot of carbon fiber as electrode material for like microbial electrochemical cell. Yes, there could be some diet in there, like even in anode electrode. Suspension that actually can further boost the process. So you are right, but that may not be just diet. So we have to actually understand one thing. Diet was kind of a trigger, okay? There, like we were encouraged to add lot of different types of conductive material, but not necessarily all improvement is you see it's actually coming from diet. There are from the microbial community analysis, you can provide some sort of indirect indication. So if you do 16S rRNA sequencing, you are going to know, okay, what kind of microbial communities are there, but that doesn't confirm that what pathways they use, right? So sometimes it's hard to confirm. So we believe that it's not necessarily just the diet, it could be, there could be other I think that was a great experience for me, you know, kind of last 4 or 5 days. So it was only, I never just focused on teaching, I think in my last 8 years. So last couple of days I'm just teaching and just, you know, like not doing anything else, and that was kind of like I would say a very different experience, and I really enjoyed the time here, and I hope you also go to industry. Good luck with that. Okay, and if you know, like if you have any question or anything, even you can reach out to me. Sometimes, you know, like my response could be little bit slow, so please don't be offended. This is because sometimes we are overloaded with different things, but again, thank you, and you know, like good luck with your, you know, and best of luck with your for me. Typically I don't give lecture more than 3 hours, okay, and over time even my teaching load reduced right now, so I teach less than what I used to do before, but last couple of days it was, and the good thing is I never had actually, after giving 3 hours lecture, that evening I cannot even talk to my family, okay, I just stay quiet because I know that if I talk, then next morning I cannot even talk. But here I think I had a little bit on the first day. If you have any question, or if I can help you with anything else, okay? Huh? Oh yeah, sure.
So we'll proceed for and then we'll have exam. So it's from 12:15. Okay. So you'll have half an hour time to relax and give your brain some time to settle down.
Probably you are going to provide us good tea.
Thank you. Yeah, or you can search online, like nowadays everything is yeah, okay. Can see, but not that much actually. I'm so busy with my research program and teaching at university that rest of the time I try to, you know, spend with my family.
Okay,
so
one of my students is running with waste water treatment.
okay.
Sometimes he used to ask me,